So here's the rotating cube again. Let me zoom in a bit as well, so we can see what's going on there. So this time I made it a bit larger, and I also added a function to the setPix, or added an if statement to the setPix function so that we don't draw outside of the screen, so it takes a bit longer now to set the pixels. Now if you go to REPL and type this command, something happens. And the thing that I did now is that I loaded a native library that does the line drawing, and instead of the one that is written in Lisp, we now use this native library for the line drawing. And that is much faster because, well, it's in C and it doesn't have to do all of this jumping around in the heap and so on, and all of the checking. So the interesting thing here is that this library that does the acceleration now is not in the VESC firmware. It is in a standalone C file that is compiled on the side and that we have loaded now during runtime. And I will show, first I will show how that works and how it is going to look if you make an implementation like that, roughly. I mean, this is a very early version, so a lot of functionality is missing and I might change things forth and back, but I think so far it is super promising. So essentially what we have is, if you look at the, let's see, I messed a bit with this one, but if you go to the examples and then look at the OLED cube native example, then we can see that compared to the other one where I had this line function and this pick set function, we have replaced those two with these things now. So we have some sort of array here, and then we have this load native lib call that uses this array, and then we have the line function, the same thing with before, but instead of drawing a line here, we pass it to this ext draw line function now. And the thing that happens is that when we load this one, we will pass a pointer to this array as a function call to C, and then it will call this function, which will means it will end up in this memory. And what this memory does is that it registers an extension in Lisp that is, well, this extension that takes a pixel buffer, or an array in this case, and 4 coordinates to draw a line. And then when you call this one, it will call a function within this memory because that's where it's registered, and it will draw the line to the pixel buffer, and then we can draw it as usual. So the code that does the rotation, everything, and drawing the edges is the same as before. So we only replace the draw line function because that is the one that takes a long time. All of the rotations is on, they don't take that long. It's really when you have to push every single pixel that you start to spend a lot of cycles and jumps and so on. Now, so we got this array in here, and we can use this as a library, and we can have more than one of these in here and extend the code in more ways than just this way. So that is really interesting. And the way it is done, I pushed this just now, so if you go to the source code, the VESC source code in LispBM, then you have the clibs directory here. And then we have some files. This was actually, once I have figured it out how to do it, it wasn't that complicated at all. So I have those files, and then I have 2 directories with examples. And the interesting thing here is that these things and examples, they are actually completely independent from the rest of the code. So what it does is that it compiles a binary that can run on ARM that is very simple. It doesn't have any start code, and it doesn't have much at all. So it only provides a few functions, and then the VESC code will call one of those functions with a few function pointers, and then you can use those function pointers to do things like register Lisp extensions and print things to the console, and soon you will also be able to do motor control commands and start the GBOS threads and so on. So if you go to the example folder, then we can see that we have a file with code and a make file. And if we open the make file, let's see where it went on my other screen. If we open the make file, we can see that it is very simple. So we only have the name of the target and the sources. In this case, we only have one source code file. And then we have a path to where this directory is, and now just up one level. And then we include the rules.mk file from this directory, because this tells it how to compile it. And the reason that this is generally tricky, actually I will go into that later, I will show this first. So that's what we have, and then if we open the code, there is not much code really. It is just a few lines to make this happen. Not the thing that is on the display now, but just to register an extension that returns the number 11 plus the number of arguments that you pass to it. So what you have to do here, you have to use this init function macro, because this will make it end up in the beginning of the memory. And then it will give you an argument with those VESC interface function pointers. And if you go up one level and open the VESC interface.h file, then you can see them here. So this is what I have done so far, but I will fill this one with more function pointers. Now, one thing that is a bit tricky here is that you cannot really use local variables here. Well, you can use if you did like this, because then this will end up in RAM. But if you later, like I planned to do, make it so that you can load this code in Flash, then you couldn't use them because Flash is not writable. So what I did here is that this thing is just a memory address that I have freed in the linker space, and then I just write this one here, and then we can use the interface functions from anywhere in this code. We don't really need it in this example, but this will be useful later. I might change this if I come up with a better way. The best way would be, of course, to make it so that when I put things here, that it will end up in this fixed memory location, but I couldn't figure out how to make GCC do that. Okay, so if we compile this code, then you need the normal toolchain for compiling ARM code as well. We'll go into example, open a terminal, and then just type make here. Then you see that you got a bunch of files. And the file that you need to include here is this example.lisp. There's also a few lines of Python code that takes the binary and makes this array here. And you see that the code that we just compiled here, that turns into an array like this. And I can take this array and then I can copy and paste it into this program. I would just keep the rest the way it is and add another thing here. Let's add it here. And then we can use the same thing here as well, so we know another native library. And when you call load native library, the thing that happens is that it will call this function, and in this case this function will register this extension that we can use from Lisp, but it could really do anything. So after this point we should have another Lisp extension that we can use. So I haven't uploaded it yet, so let's see first. The name of the extension is extension test. So if you type that one in here and don't give it any arguments, then you get evil error because it doesn't exist. But now if I upload this code again, you can also take this one here to see that it still runs the other native library at the same time. Now we do the same thing. And we still got evil error. Yeah, because I didn't put in the correct name. I loaded this one twice. Interesting that that even worked. Wait, let's see. Yeah, so now you see that we had 11 plus 3 arguments, which would be 14. So now you have another thing that we can use from Lisp. So the interesting thing here is that you can kind of see, you can load many of those things, and you can kind of see that like the Lisp interpreter, like the shell of the VESC operating system, if you call it that, Or you can load a bunch of programs and set them up and make them do things. And if you have things that run, for example, Tribio as things, then you can run multiple of those programs at the same time if they wouldn't interfere with each other by, for example, sending the same auto commands or using the same ports. And yeah, so that is really easy to get running. Now I can mention a few things about the technical details. So the reason that this is tricky is that usually when you compile C code, then and you put some functions there, then it will generate some assembly code, and those will be put somewhere on fixed addresses by the linker. And the code will also assume that, for example, when you call this function, or let's open the other one that is a bit more that has a bit more code in it. Yeah, we can also have a quick look at this one, by the way. This is one that does the line drawing, so we have this init function again, and then we register this drawLine extension. And this drawLine extension takes the arguments, and then it will extract them, and then it will use this drawLine function that we have here that runs the same algorithm, and then we also have the setPixel function up here that this one uses. So if we look at this one and compile this normally, so when we enter, when we go here and we call this function, then it will assume that, or actually let's explain here because it actually doesn't call it, it registers this, then Lisp calls this one. But if we are in this one and we get here and we call this drawLine function, then normally it would say that, okay, I know that drawLine is in this address, so I will jump to this address now. But when we paste the code into the VESC like this, we don't know this address when we compile this because it might end up anywhere on the memory. And one way to work around that is to compile with a flag that makes position independent code. And this also has to go together with the linker and everything. So instead of making the assumption that you know which address this one has, you make the assumption that you know which offset this one has. So if you are here, then you know that you have to jump this much upwards, or however many instructions that will turn into, in order to run this one. And this way we can compile some code that is independent of where it is loaded in memory. And if we look at, let's see, the rules.mk file, you can see some of those things, and it's not super many flags. I mean, this one was the main flag to make it position independent, but then also with the linking to get it to work with all the standard libraries and everything, then I also had to add some other things, and also these here together with these were quite important, especially if you use the standard libraries to strip out all the functions that they're not using. And then when you strip them out, then you will get nothing left, so you also have to tell it to assume that the init function is going to be used, because it would assume that if you do that, as we don't have any start files, and then the application doesn't have any entry point, and then it will assume that nothing is used, and then you get nothing left. And this took really forever to figure out, and maybe I will improve it so that I can do the linking differently with the static variables, as I mentioned before. But even so, it's not that bad, and it would work if you only load this library to RAM and not to Flash. Can't even load it to Flash at this point, but I will add support for doing that in the near future, hopefully. So that is how this part works, and then we also had to figure out how to make a linker script for it and learn kind of all the things that the compiler generates. And in this case, I just say that I have one memory region that starts at position 0, and it is 64K long. So if you generate more code than 64K, it will tell you that the memory got full. And then I had to figure out how to place all the things that the compiler generates appropriately on that memory. And that's also something that I'm not really used to and took really long to figure out. And there is not a lot of information on that on the internet that I could find easily. So yeah, so it was nice to get that figured out. Now, next thing is that when we are here and we have all of this code, then yeah, everything here is position independent, but we also want to be able to do things like print and use other things, like I said, with those function pointers. And that is why we pass them as function pointers to the code in this list is struct with function pointers. And the nice thing is that these pointers will be set before this code is called. So even if you have some different version of the VESC firmware with different compilation flags or something, or different memory layout, because they have dual motors and so on, they end up on different addresses. It doesn't really matter because we set these pointers up to whatever this firmware has. So this thing is really independent of the rest of the firmware, as long as well, it is reasonable enough and similar enough to set up the struct in the same way that it passes an argument to start the code. Let's try to, well, we're at it. Let's also try to print something. I can demonstrate that. So we can go back to this simple example. I can also mention this going a bit all over the place here. So when we call the init function, this one, well, when we build the code, it will call this init function, and this init function will return something, and what it returns is a stop function. And if you, for example, would set up threads here, which you cannot do yet, but we will add that possibility soon, then you can stop your threads here and wait for them to be stopped, because maybe you're about to upload new code and then it will overwrite this code while it is still running, and then things will crash. So yeah, I can also mention the thing about crashing, that it is not as bad as writing the firmware directly, because if you upload something that crashes, which will hopefully cause a watchdog reset, then on the next boot you will see that the watchdog did reset this one last, so it will not reload this application automatically. So hopefully you can experiment with this without the debugger. But yeah, if you're gonna compile and upload C code, you can always mess up things, because you can really poke around anywhere in the memory. So then you should have a debugger at hand and be a bit careful. Yeah, anyway, so let's try a print function. So we can use this, and then, for example, when we do, let's just do it here. When we load the extension, we can use this one, and then we can do printf. And that's also nice then, that even if you use printf here, which uses all of this stuff from the standard libraries to make the arguments work, this code doesn't really have to be aware of it, because we just pass it some pointers to strings and variables. So it will not grow that much even if you do that. So do hello world. Save this one. And while we compile this now, I can also open the lisp file here to see that this one will grow slightly now that I run make. And reload. And I think we got another 2 lines, so let's put this one in here, replace this one. And now when I upload this code, then when we go to the get execute this line, then it should print hello world and init function down here. Let's see if that works. Yeah, that seemed to work. And you can also see stop in code, which is something that the other thing printed when we run the stop function. But you can also, the stop function can also be empty if you don't need it, or you don't even need to return a stop function. You can also return 0 like you do in the code here, and then it will not even try to call it. And that is okay if you know that nothing will be running when you leave here, which is the case because this will only run if you call them from Lisp. So yeah, so one big plan that I have kind of with this stuff is that when you have something like this, then you can maintain applications and libraries that even are written in C when they need more memory and more performance, and have them independent of the VESC code, because you don't need to, you only need to respect the interface that I'm hopefully gonna keep stable enough to not make that a pain. And you can also do things like write drivers that you can later on easier use from Lisp, like a nice display driver that can do more than just drawing lines fast, for example, in this case. And then if you want to share them with someone else, they don't necessarily need to have the burden of setting up the toolchain and everything, because they can just take your code and paste it in like as an array like this, and then they can use this library. And later on, when we have a set of libraries, then they can even maybe make some kind of we can have them, for example, on my GitHub, and then you can make pull requests to put, for example, your balance application there. And then when people find it, you can even make it so that you can just paste some link into VESC Tool, where it will download that and upload it to the VESC, and then you get the application running. And you can also pair that with some QML UI that you get that way, and then it will work on any VESC-based hardware. So hopefully that works out. Yeah, that's what I had for now.